Low-density parity codes for us normal people, starting now. Hey guys, good afternoon. My name's Jason. I'm KC5HWB. This is Ham Radio 2.0, my YouTube series. If this is your first time to join us, click on the subscribe button below and the bell notification icon so that you can keep up with all the videos that we post on this channel about anything and everything that's new in amateur radio. Today is the next episode from the TAPR Digital Communications Conference from September of 2018 and is given to us by Michelle, W5NYV, New York Victor, November Yankee Victor. And she talks about low-density parity codes for normal people, so she puts it down into layman terms, as it were, so that those of us who are not familiar with that, which I have to include myself in that, can understand the presentation a little bit better, so I hope you enjoy it.
All right, this is called LDPC for normal people, but I have a confession to make.
Are you ready, Jason? Yeah. Okay, go ahead.
There's something on this slide I don't know anything about, and it might be normal people. I'm sure some of you have the same problem. LDPC stands for Low Density Parity Check Codes. Okay. Who am I? I'm W5NYV, Michelle Thompson. I have a master's in information theory from USC. The way that I explain that is it's icky math. That's what I do. Active in IEEE Info Theory Society, and forward error correction is a big part of info theory. LDPC is one of the best forward error correction codes that we've ever made. I talked a little bit earlier about Open Research Institute. Phase 4 Ground Project is one of the projects of ORI, and LDPC is a core technology that we are bringing to the open source community. And you all need to know about LDPC codes. If you care about forward error correction, and I know you do, then this is something you need to know about. They were discovered in 1963. Robert Gallagher did a PhD dissertation, thesis type thing. It's not too often that PhD work has such lasting effect, but it almost didn't happen. It was so impractical to implement, and there were so many other things going on that were so different that it was promptly lost. Gallagher coded it up and ran it on an IBM 7090 in 1963. The block length was 500 bits long, and it was simulated with a very large probability of error to force an error quickly. And it still took, and he used one code word, and it still took hours to run. That may have been a reason why it got overlooked. A while later, in the 80s, a guy named Michael Tanner, he figured out a way to represent low-density parity check codes in a graphical form. And this has turned out to kind of be the killer app for LDPC. It gives you a lot of traction and an understanding about them, and we'll learn about those today. So it was still impractical to implement. It was lost again. So third time was a charm. 1996, Sir David MacKay wrote a paper, which we all still read in the community. It's a foundational paper. It started getting a lot more interest because of the massively parallel structure was finally able to be implemented, and real practical applications were possible. One of the biggest things is that it was chosen for DVB-S2 standard in 2003. The S stands for satellite, so this is digital video broadcasting. You're probably familiar with DVB-T and T2. S is the satellite version, S2 is the second generation. It was kind of a big deal. LDPC is now used in a wide variety of applications. And since 2003, we've seen LDPC sort of take over from turbo codes in terms of general performance, better error floor, and especially at high code rates. Turbo still does really well at lower code rates. There's an enormous amount of academic research surrounding LDPC, turbo codes, convolutional codes, block codes, and we are still finding out new stuff all the time. Why are they so good? Well, if you use these codes with something called iterative decoding, meaning that you make a couple of runs at it, it's cyclic. You don't just, do a multiplication and call it. It's an iterative process. If you do that, and if you use something called belief propagation, then you can get a fraction of dB from something called the Shannon limit. These are implementable decoders. One of the foundational things about info theory is that you can get close to the absolute capacity of the channel. It's called the Shannon limit. But we don't guarantee that there's an implementable code. We just tell you that you can get there. They don't need interleavers. They don't need a trellis on decode. That means you can make a massively parallel structure and go kapow. They have great block error and burst error performance, and the error floors occur at lower rates. Error floors are kind of weird. When you get a high SNR, you expect your code to continue to improve. But these improve. There is a point in time where there's an inflection point for improvement in performance. It's very weird. It flattens out. It doesn't do quite as well. That's a hallmark of the structure of the code. Picking a good code means that you eliminate the error floor or you put it below anything else you care about. The decoding complexity increases linearly with the number of entries or the number of ones in a parity check matrix. So you want to keep it low because you want your complexity to be low. And also another cool thing about these things is that a single code works in many different channel models. And that's kind of cool too. And this is a bunch of words, and if you're not in the field and haven't worked with error correction or forward error correction, it may be kind of like, oh man, it's a bunch of gobbledygook. And whenever I'm encountering something new, I like to think of the thought being the language. This is by Wittgenstein. A technical vocabulary is merely a language within another language, and a consideration of this technical vocabulary is you attempting to discover the reality that the words disclose. So if you get confused, just let the words flow over you and let them just kind of sink in, and it's going to get better. By the end, you'll be appreciative of these as I am. So what's the trade-off? I said lots of good things, right? Well, there is a trade-off. There's a lot of factors that affect the quality of the code, and we're still kind of figuring out new things about them. In a lot of cases, it's really not straightforward, and the longer that you get and the more complex you get, the more weird things you see. The code construction is challenging and surprising. So these codes that are just a couple of hundreds of dB away from this limit, they were found by computer searches, genetic algorithms, or just sheer brute force searches. And something that kind of upset me when I first started learning about LDPC was this quote from this book: "Code design and construction are more of an art than a science." And I went, the hell with that. This is all supposed to be science. This is all supposed to be math. So I was, I have to say, just a little bit outraged, and it made me read the rest of the book. And by the end of the book, I went, wow, they were right. Now, we do have an error floor because of trapping sets. The error floor is when the code stops improving with really good signal to noise. And trapping sets are these really cool little things. If you've ever done like a state diagram and you get like caught in a little loop, or, oh, those unused codes in your state diagram, you better have them circulate too to deliver you back to some known spot. And if it doesn't, then you're stuck there forever. If you've ever done that with code of any type. Well, trapping sets are the similar sort of structures inside LDPC, and that's why we have bad error floors on occasion. And the encoders are complex. It's weird because sometimes the decoders are usually almost always the complex thing, but the encoders for LDPC are non-trivial. So if you have a short code length, go ahead and use a turbo code. Everyone has their one true slide, and this is mine. This is my favorite one true slide. So what is on this slide? Oh, look, I killed the battery. But I have a backup. I've explained my aura before. I'm sorry about your remote. Yeah, so along the bottom here, this particular thing, you can think of this as signal to noise ratio. It's got a fancier name, energy per symbol divided by the noise power, all of that sort of stuff. But this is essentially signal to noise ratio. And over here, this is how many bits we can cram through our channel. Now this line here, this is actually, that's it. That's as good as you can get. Sort of intuitively, you can tell that if you have a really booming signal to noise, you go up here and you find out that bang, that's as much as we can cram through that channel. That's a lot. And sort of intuitively, if you have a very low signal to noise, you can barely hear the signal, then you sort of kind of intuitively expect that you can only get so much bits through your channel. The surprising thing to most people is that you can't get over here. Can't go there. Troll is guarding the gate. This is as good as you will ever get. Now, this doesn't just work for transmission, it also works for things like storage. So anywhere where you have information, you have a limit, and it's roughly based on the signal to noise, and over here is the, so when you hear people talk about getting close to the Shannon limit, that's what they're talking about. That you have no more that you can get. You've gotten as good as you can get. Now, why would you want to do this? Well, in DVB-S2X, the X is for extension, because even though this standard is so awesome, they still had to put an extension on it. They have something called ACM. It's adaptive coding and modulation. And what you do is you adjust as your channel changes, or as your position changes, or as your bandwidth needs change, or congestion, that you can make adjustments to your error correction coding and even your modulation. So you get the best possible throughput no matter what your channel conditions are. Now that's pretty cool. In a traditional system, what you do is you pretty much pick the worst case signal to noise, and then you go over here and you go, okay, how much bandwidth do I expect? And like which codes over here in the nice part, the achievable part, which codes can I do? And you're kind of stuck with those. With adaptive coding and modulation, though, you just ride this line. These things here are from the DVB-S2 and S2X protocols. The dark is all the different combinations of all of the code rates and all the different modulations that you can pick out of the standard, and the purple is an actual implementation on a USRP. Now you see there's not much daylight here between the Shannon limit and an actual implemented LDPC-based system. Why do we do all this? Well, it's all about the matrix, right? Say we want to send a digital message in a systematic and orderly way, and we use linear block codes. LDPC is a linear block code. And they're super awesome at this. We get our messages, we figure out how many, and we make a list. Now we notice that there's some unnecessary redundancy in here. Alice is really talkative. Bob says the same thing over and over again. We clean it up, we fix this. All error correcting codes, this is your first step. Just like with big data, you have to clean the data first. You get rid of any unnecessary redundancy. You got to figure out, what are you trying to say? What alphabet are you going to use? Now, there's lots of ways to remove redundancy. We're just going to skip right ahead and say that we did it. The K here is the length of the code. So I've figured out that I just need 4 bits, and 2 to the 4th is 16, so I have 16 total. Yeah, that looks good. Now, what's the big deal? Just send them. Well, if you have no noise or interference or any other issues or any loss in your system, that's fine, but man, you got noise and trolls, and they're going to mess everything up. Why we have forward error correction. Okay, what do? Well, we take these messages and we're going to transform them into code words. We're going to put back redundancy. And we took out all the unnecessary crappy redundancy. Now we're going to put in a good type of redundancy. These code words are now each longer by a fixed number of bits. We've spread them out in math space using special math powers. We got some breathing room in there so that each bit in the code word, or resulting code word, can get knocked around by the noise. And we can sort of round off to where the correct code word was. It'd be sort of like if all of you are kind of spread out in the room enough to where you are not knocking into other people. You each know where you're sitting. Math space, the vector space for these code words, is pretty much the same. We are spreading everybody out. Now, it's a lot of messages to store, though, especially if we have thousands and thousands of code words. Is there some sort of clever trick that we can use? And how do we get those spread out code words in the first place? Well, we use our math, our special math. And the magic is all in the matrix and the matrix math. And so the page that's handed out has the 2 related concepts that we use for this sort of stuff. So you have a vector dot product, where you multiply, you have a vector, and you multiply the first 2, and you get a result, add it to the multiplying by the second 2, add it to the result. Look on the little paper and it'll make more sense. If you multiply a matrix by a vector, you'll get a vector. It's a bunch of dot products. So the super special powers are contained in the structure of something we're going to call G. So we have one of our 4 bits here, and we have constructed this matrix. And the neat special power about this is that all of these are linearly independent. All you need are a small subset of linearly independent code words to make all the rest of them. And this is pretty cool. Now there's some linear algebra is the field of study where this comes from. Linear independence is awesome. So any code word added to any other code word is still a code word. You can only go to another code word, and there's space in between them, and that space is pretty critical. So here we have G. How do we get the original code word back, though? After we've used our cool G, to create, our spanning set, to create code words. We've sent them, we've got them, they've got all the good redundancy in them. Well, with another matrix. So G usually stands for generator matrix. That's the one you're going to use to generate the code words. Vector times this gives you the right type of vector. Well, it's actually composed of two subvectors. There's something we call P, and there's something called identity. So this is the identity. Notice anything interesting about that? It's got a diagonal of ones. An identity matrix is just like you would think if you remember, identity from math. 1 times anything is anything. This is the same sort of idea inside matrices. It's an identity matrix. And over here, these are essentially the equations of the parity bits. They add the extra special space to our messages. So in order to get the matrix that undoes all of this, here they are, matched up, we do this. We switch them. And we do something called a transpose. We flip it along the diagonal. You end up with this. So there you go, Bob's your uncle. There you go. You have a matrix that can undo the code word on the other side. That's pretty cool. That's just like pretty simple, right? It fit on a page. So the parity check, this is called H. And it's some more technical terms. It's in the null space of G. That means that any code word generated by G, when you multiply it by this, is 0. I get a good code word, I multiply it by this matrix, it better be 0, or there was an error. This turns out to be very convenient. We call it orthogonal, too. If you hear the term orthogonal, that means the same sort of thing. Okay, so we have our matrix. We're going to use pink for parity, because we like parity. So we received a code word. Now we're going to check it. Now, first thing we have to do, clean up our act. We have to transpose H so it's the right dimensions to multiply by something that's n bits long. Don't worry, we do this all the time. It's just flipping it over on the diagonal. And we have a valid code word, but the international symbol for wrong is red. So here we are. We have managed to get enough noise, and we have a bit that's been flipped. So what do? Well, we multiply our received vector times H transpose, and we have a 1/7 vector times a 7/3 matrix. It gives a 1/3 result. Those better all be zeros. If it's not, like I said, you have an error. What you do in practice is that you generate a table. Depending on those 3 bits, what that result was, you look up what the error vector was. Now, there actually are many, many solutions for the error vector. What you do is you pick the one with the fewest number of errors because it's the most probable one. And it's like, wow, that sounds like common sense. Ever so often, math has common sense. So this is what those parity check, those 3 extra bits kind of look like when you multiply them all through. This is a sort of XOR or modulo 2 arithmetic. So it's kind of pretty, right? You can see that they're all intertwined. You cover the whole vector with those 3 extra bits of parity. That's what it looks like when you squiggle it all out. In our case, we did not get 0. We got this. It's called the syndrome. Now, we can use it not just to detect, but to correct errors. Like I said, you have that table. It'll correct up to a certain number. You will definitely run out of steam. Because as you imagine, if, say, you're a code word and you're an error enough to move you all the way over to his seat, you're going to look like him, and I'm going to think that you're him, or that you're you, or that you were you. That can happen. When that happens, your code words are not far enough apart. You're going to need way more redundancy. You're going to have to spread them out in math space. That's why codes are designed for certain channels. So, this is what a low-density parity check matrix looks like. Low density is sort of a squishy term. When we say low-density matrix, this is actually a very tiny LDPC code. We mean that we have much fewer ones than a typical parity check matrix. The fewer ones, the better, because the complexity goes up with the number, linearly with the number of entries in the matrix. Okay, here's our H. Unlike other block codes that we've talked about that you're now totally expert in, you actually start with and you define your LDPC code not by the generator matrix, but by the parity check matrix. That's somewhat unusual. And at first it sort of sounds like low density doesn't mean that it's as good, right? Like it's sort of non-intuitive that something with just a few sparse little ones every now and then would be good. But you'll see the power here. You can tell a LDPC matrix by something special. Each row has the same number of ones. Each column has the same number of ones. Any two rows and any two columns have at most only one in common. And that's an LDPC matrix. So you can spot it just by kind of testing. Now, a truly enormous matrix, you can't tell by eye, but you can sort of test it here. Each column has 2 bits. Each row has 4. And you can pick any 2 and you can test it. It only shares 1 in common. This means that when you run the math through this matrix, the fact that only 1 in common, it gives you tremendous gain, essentially, for lack of a better term, or tremendous leverage on the math. So the number of columns corresponds to our code word length of n. If you have 160,000 columns, then you have 160,000 bit long code word. In our case, we don't have quite that many. So the number of columns is the code word length. Each row is used to produce a parity checksum. So remember before we multiplied the code word by an entire parity check matrix? Here, each one of these rows is a parity checksum. We use a dot product to figure out the sum. So how do we decode? There's actually several ways. Once you get this matrix, either you generate it or you find it or you construct it or someone hands it to you. You can use majority logic. That's fair. That's a hard decision. You can use bit flipping, where you just kind of you try stuff and you see if it works. That's another hard decision method. There's something called weighted bit flipping. This is sort of caught halfway between the hard and soft decision styles. You can have a posteriori decoding, kind of hard to pull off, or you can do iterative decoding based on belief propagation or some product algorithm. Okay, so which one looks the hardest? Yeah, let's do that one. Want to do that one? Yeah, let's do that one. Okay, so first, we don't multiply like we did before. That would be way too easy, right? We use something called a Tanner graph, and we use some equations. That's what we're going to be doing. So in general, this is what a Tanner graph looks like. It's called a bipartite graph. This is what we are dealing with. First, we get our sparse H to look like it should, and then we use this as a map to come up with the math, and then we do something called iterative decoding, cycling back and forth, doing the same thing in a loop until it works. So we receive a code word, we decide what we think we received as a probability. We pass that to our parity check nodes. Those are going to be the subcode nodes over here. And we process various combinations. We feed the resulting back to our digit nodes or bit nodes, and they process some more. They feed it back up the graph. So you can see this is where the messages travel back and forth. And these are our parity sum nodes, and these are our bit nodes. This is just a general graph. So like, what would it look like if we actually built one for LDPC? Because bipartite graphs are used in all sorts of places. They're really cool. You have a function, and you would like to break it down into factors. Then you can use this as a factor graph, and the variables that they share can be mapped out. And boy, can you solve some nasty problems that way. Well, we use something that is one of those graphs, but we have a kind of a special sort of flavor for LDPC. So we have J rows, J check nodes, J parity sums. We have N columns, N variable nodes. Okay, so what do we do? Let's take this top one. This is S1. We have 1, 2, 3, 4, 5 of them because we have 5 rows. If a 1 is here, we say it's attached to a V1 bit node. We have 1 in the second and third and fourth, and so we just connect first, second, third, and fourth. Does that make sense? Okay so far. Okay, we move on. We go to the next row. And we have, let's see, we have a 1 here, and we have a 1 here, and a 1 here, and a 1 here. We know we're going to have 4. Okay, it connects to 1, connects to 5, 6, 7. So we can sort of see we're building up the same sort of structure from bipartite graph, but we're using the bit positions in our parity check matrix. Hey, cool, it's kind of pretty. Okay, once we're done with that, this is like the cooking shows where they go step by step and then they leap ahead and they pull it like completely done from the, yeah, that's what we're going to be doing. Okay, now a regular code means that the number of ones is constant for all the rows and constant for the columns, and all the code bits are involved in the same number of parity checks. And all the parity checks are involved in the same number of code bits. But you can have an irregular LDPC code. And an irregular LDPC code, those things aren't really true. Some of the bits are involved with more sums. You know, some people get around. They're involved in a lot more than they should be. Now, what is the advantage? Well, certain bits get a lot more attention. And an interesting thing happens. You punch right through. It converges a little faster. You can get good results. DVBS2 actually uses an irregular LDPC code and not a regular one in order to give it an extra little boost advantage. It can backfire if you overdo it, just like if you hot rod your car a little too much and you put your foot into it a little too hard, you may end up wrapped around a tree. Same sort of thing in code space, except it's all wrong. Okay, so, hey look, data. So now we have this graph, you know, and this is really kind of an abstract concept, but it's very powerful, and it stands for the actual equations that are running in code on the machine that is doing all this receiving. So we're going to get some data, and we're going to say that we're going to use BPSK, and let's just say -1 is data 0 and 1 is 1. These are actual voltages that are coming in. So we have all these negatives, and oh, look at that. Okay, I have a suspicion that that may not be right. I don't know, maybe because I wrote the slide. But you know, we get all these values, and we, as a designer, and because we've studied the channel and we know what we're doing, we know what the real values should be. We should be getting 1 or -1. With no noise, we should be just getting those two values. We know this. Now this gives us a special sort of power, because we can use something called a likelihood. If we know what we're supposed to get, then we can come up with likelihood. I'm going to probably mess up and call these probabilities, but they're not truly probabilities. They're really all likelihoods. And so it looks bad, but it's really actually pretty simple if you're in an additive white Gaussian noise channel. Channels are not really additive white Gaussian noise, but everybody that actually does any math, that's what they're going to use because it's pretty close. If you actually go in and look at real channel models, it's much, much messier, and that's a whole field of study to kind of get that last bit of performance out of the channel. But we're going to do it easy so that we don't have an equation that is literally like this entire slide. We're going to use one that will get us pretty close. So what does this help us do? Well, you know, intuitively, -1.1 is pretty close to -1, right? Like, I can assume that that's probably right. But like, what do I do for this? It's almost halfway between, and what do I do for that? You know, and what happened here? You know, that's a lot of noise. Okay, so we run our little math. 2 times our received. Sigma squared is the noise variance computed from the received SNR, determined by channel. So we're going to, because of additive white Gaussian noise, we get to know this. We don't have to go figure that out. So here's our results. That's what we get. And then what I do, even though you do normally stay and you add instead of multiply, and you know, are we going to use our matrix anymore? No, we really don't have to. We're going to sneak up on it and replace it with our bipartite graph. So what I did is I just replaced it with probabilities. Like how sure am I that this thing was, in this case I think it was a 0. You can see, I'm not really that sure here, and I'm really, really sure here. I just considered this to be saturated. Okay, Now, a neat thing about probability is that you have a probability of one thing, and the other thing is the opposite of that, then you know both of those probabilities, because probabilities of those sorts of things that are independent, that cannot possibly overlap at all, adds to 1. So I just go ahead and do that, and I get both results, because I'm going to need both as I decode. What I did here is kind of like, okay, just to make it more visually obvious, the dark ones I'm really sure and the light ones I'm not. Okay, for each bit node, we now have probability it's a -1 and probability it's 1. They add to 1. We're good so far. What do? We send those probabilities, the result of each one of these bits. This is our code word, bit 1, 2 through 10 of our code word. And I've done like how likely is it that it is what it appears to be. I'm going to send those. Each is going to go up the line. All of these, all the messages go out up to the checksum nodes. Okay, and so you can see the one I'm not so sure of goes here, and it also goes here. And that's kind of our secret weapon here. It's all interleaved. And you can see, it's all scattered around. So let's focus in on one checksum. Keep in mind that what I'm going to tell you is also happening in each one of these. And it gets messy like a plate of spaghetti very quickly. But we'll focus on this one first. So we sent them up, and now we're going to do some work up here. This has processes running in it, essentially. Think of it as like a little teeny computer. We know that if we have a correct code word, that this should sum to 0. And that's how we construct some math to go back down to the bit nodes. We know that if it's 0, there was an even number of 1s that were delivered. 0 is an even number. And we kind of know that this one is not exactly right. So we have 3 high likelihoods, and we have one that's kind of like maybe a little iffy. So you know how it is. You have an even number of children, and one doesn't really cooperate, like at the grocery store. So what do? Well, the S1 tells each bit node back how probable it was that there were 1. It's like a parent telling each child what the other children thought of them and maybe how they should change. The key is that S1, when it talks back to these nodes, uses only what came from the other nodes. So it's like children ratting on each other, So hey, variable 4, variable node 4, child 4. Let's assume that you're a 1. This is how this works. If you're a 1, then there's either one more 1, or there are 3 other 1s to add to 2 or 4. You're all 1s. You can't be the only one. And we can't have you be 1 and 2 others be 1. That would be 3 1s. It's like who's on first, really. But in math, it looks like this. And it's a little easier when you say, okay, here's the likelihood that it's 1. So here's my 1, 2, 3, 4. That's an even. Here's 2, and these are 0. So we just construct that situation that we talked about. You need an even number of 1s to make this work. Now we're going to get a number. Our result back to you, node 4, is going to be 0.35. So you better shape up. This number here to this V4 was composed of the information from these nodes sent here, and now it's going to send it back to this one. It's going to do the same thing for all of them. So now we've updated our bit nodes. And we're doing this in each one of these. Okay, so this is happening, it's not just happening here, it's happening all in parallel. Now the real power, now we're going to go back. Now we have updated numbers for each bit node. Now we're going to do some more math and we're going to send it back up. The real power, though, is here. for this guy, it's connected to these two families, you know, so it's not just you pissing off these siblings, you know, at the restaurant or whatever, but you're also pissing these off. So they're all going to snitch on you. And boy, does it makes a big difference when you set up math like this. You know, you get lots of leverage. Okay, so we are going to send, we're going to send the updated probabilities back. We got new numbers, and now we're just going to send them back to those nodes. Now, the interesting thing here is, look, when we say we're going to send them back to the nodes, there's these other connections. When this transmitted back down to here, here, and here, oh, look, I also got a message from here. Oh, interesting. So now you can see where the spaghetti is starting to happen. It's spreading. We started out with information just from these four going to here, and then we ratted back down here, but this one also ratted, and now this one has more information. That's really the key here. Okay, now we go back. Something else that we have to do. Since we're multiplying, and we're multiplying likelihoods which are all less than 1, whenever you multiply a bunch of numbers that are all less than 1, what happens? The number starts getting much smaller. Every generation we're dealing with tinier and tinier numbers. And if you know computers, you know that they don't really like you to do that. They would really like for you to stay within the range of the variables or the registers that you have assigned. So what we have to do is use something called K. Okay, so what we do is every time that we do this back and forth, we normalize. We know they add to 1, and it's a real simple equation. We renormalize. Everything stays within the right range. It stays a good likelihood. So that's something we have to do, or else within a few iterations, you're dealing with 0.000 whatever and tilt. Here's another way of looking at it. Here's all the parity check nodes that are affected by the first 4 bits. So it was pretty obvious that since V1 is also connected to S2, they're involved. But hey, look at all these other connections. You can see that very quickly, we have involvement from everywhere. All right, and now everyone's snitched. The check node to the variable node actually starts an iteration. Now, you know, I'm like, but we started here, right? That's actually, they call it the 0th stage, where you do the little likelihoods and you get them up there, you know, because all the first set depends on is your received code word. So that almost doesn't count. Whenever we talk about iterative receivers, it's the messages from the parity checksums back down here that starts the iteration. Now and then when it reports back up to these check nodes, that's the other half of the iteration, the 2 stages. So this back and forth continues until we reach a threshold probability. Here I used probability. I'm just going to go ahead and say it. We reach a threshold probability. Our numbers cross over some threshold. And for LDPC, it's usually 0.5. Either we reach that threshold or we run out of our maximum number of iterations that we have set. And you really want to do that because there are sneaky little things in LDPC that can cause you to oscillate. Those are not the best LDPC codes, but you want to avoid that. You're going to be close to the right answer, but you don't want to be bouncing around forever because you just can't quite close the deal. So you set a maximum number of iterations and a threshold. If you reach the threshold very quickly because you don't have very many errors in your code word or none, then you move on very quickly, right? If you reach the maximum number of iterations, you know, you design that in so that you're not choking your system down. So this sort of convergence, like how quickly can you get through these iterations, like how many you need, this is a very active area of study with lots of icky math. So what's after LDPC? It's so awesome, right? Is it the last code that we'll ever need? No, it's not. There's something called polar codes, where you set up virtual channels within the code. 5G uses polar codes, by the way, so if you're hearing about 5G and get a 5G phone, you'll be using polar codes every day. You put the data bits in the most reliable channels. So not something that we've seen in any of these other codes today, where you're putting the data bits into a different channel. With regular linear block codes and with LDPC, you're pretty much stuck. And you have subcodes in LDPC, but those are set by the matrix, right? This is kind of new. you're going to put data bits in the most reliable channel. Huh. Well, what does this get you? Well, it's the first code that's been explicitly constructed to achieve channel capacity. Now, this is a simple channel, but this is a channel model that's used in all sorts of stuff. This is in Wikipedia, so it must be true. And I talk to people, and it turns out it is. This is super exciting. Okay, so the downside, well, there's not a whole lot of them, that has modest complexity. So coming right behind LDPC is polar codes. All right, questions? Or what else would you like to know? What did I miss? Oh, what tools? Oh, that's a really good question. So they're used codes of various types, or particularly LDPC. Okay. Most people start out with something like MATLAB. You're going to be using, which is Matrix Laboratory, I think. So you're using MATLAB or Octave to handle the matrices because they're very, very large. And for any reasonably good code, you need to have a long code, lots of bits in it. And when you get a very, very long code, and even in MATLAB, it bogs down. So MATLAB gives you an advantage because you can actually, there's a shorthand way of crunching or compressing sparse matrices. If you have lots and lots of zeros, you can go in and just say sparse, the matrix name, and crunch them down. This is so good because it reduces the amount of processing for dealing and designing your code. So that's one tool. You really do have to have something like Octave or MATLAB in order to play around with them, or you'll go crazy. Another good tool to use is any sort of library that will let you set up searches. So if you want to design one to kind of play around and see all the different factors, how the code changes, then you're going to need some sort of library that will let you set up search conditions and let you get through searches very quickly. When you're actually building hardware, because this code is just crying out for a parallel deployment, it really is. It's just crying out for, you can do all this in parallel. It's an enormously, obnoxiously parallel decode process. Then an FPGA or an ASIC, you can do it on a GPU. And we have a version of DVB S2X LDPC decode that Charles Brain wrote for GPU, for graphical processing unit. The problem with that, and the reason why we're going to offer that and support it and promote it and publish it, and I think it's awesome, and we'll probably use it in Phase 4 ground, there is a caveat. The way that GPUs are set up and the way this code was written in order to take full advantage of GPU, then everything that you do, all the frames that you do in parallel have to have the same format. You remember adaptive coding and modulation? Well, that's supposed to let you decide on a per frame basis whether you need to change to a different error correcting code, or if that frame is going to a partially deaf receiver. Like this ham has the dish pointed in a funky way. This ham never takes care of their gear. This ham dropped it on the driveway. And this one's pristine and has an 8-foot dish. Those are very, very different receivers. So in the case of GPU, in order to take advantage of that type of parallelism, you're kind of stuck with doing the same thing for kind of a long time. The way that you solve that is you just say, too bad. We're not going to change for you on a per frame basis, or reserve it for machine to machine. So GPUs are good for this if you're okay with it, with not being agile or not being as agile as you could be. And an FPGA or an ASIC is the way to go for any significant deployment of an LDPC code. What else?
Brian?
Okay, 2 questions. You talked about art and science. Encryption, which is a related mathematical thing, is based on prime numbers, which is clearly real science-y. Are you suggesting that these codes are magic? We have to just look around and bump into them?
They're totally magic.
Are they?
They're so magical.
Then how do you
Hello
find
Kitty
them?
would never help me if it wasn't magical.
So do you just search through the space and then evaluate them and go, this looks like a winner?
It's probably less magical than that. When you're doing it like a grinding through like a search space, if you're using a genetic algorithm to find this sort of stuff, then you have an objective function and you very quickly figure out which families, which structures in there. And also Galois fields pop up here all the time, and they're magical. You know, so it's prosaic magic.
So in a related thing, it's like if you're trying to do 8B, 10B, you can immediately throw out a bunch of characters because they lack enough transitions, and then you focus on the rest to pull out those magic K characters.
Yeah, there's something similar in here. Let's see if we can get one without, well, you guys can handle color, right? So when you look at this, you can construct this to where it'll never work. So you can throw those out. And you can test for that. And it's really important to do it. Like if you go do, 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 and you can get back to here. In other words, I went 1, 2, 3, 4. If you have a path like that in your graph, forget it. So it's much like that. Like you know that you can just throw those away because those may never converge. They're going to get trapped. It's trapping sets. You know, and also if you have short loops, you know, anything that's really short, 4 is especially bad. I think there's some sort of Chinese thing about the number 4. That's probably why. But you know, you want these long paths. You know, you want it to give it enough chance without getting pulled back in. I know this is kind of. I'm going to wave my arms now. You want to get far enough away. All these paths, you want to get separated enough. You want to get far enough away to where you don't get pulled back in. Escape velocity. You know. Okay, so that's. I know it's arm wavy, but that's the basic idea.
So the final thought is, you talked about, well, if your codes are short, just use turbo.
Yes.
And obviously streaming video is long, because it has frames and things. How short is short?
It depends.
Give me of course it does, but give me a rough thing.
I have no idea. It would totally depend on what you were trying to accomplish in the channel. There's some rules of thumb, but like, since in almost every case, except for just for fun, for learning, and because icky math is awesome. In almost every case where I've actually had to go and dig in, it's the code has been specified. Like in DVBS2, the codes are specified. So the pressure is kind of off. I'm able to kind of go in and dig through. And then the smaller ones that I've designed to learn, they're so small that like they really don't work very well. You know, this one actually works pretty good, and I think this one, I believe that this one or one very similar to it is a famous code. It's one of the Hammond codes. You know, that's what you end up with. Put an asterisk there. Somebody should probably check me. I'm sure if I'm wrong, I'll hear about it. But, you know, for smaller ones, when you design them, it's like the overhead is, you have to get away from the overhead. So that's why turbo codes in some ways are way better for smaller codes. Because, wow, there's the encoder. We didn't even talk about the encoder. You know, 'cause I do decode, so I do receive, but like, I wouldn't, yeah.
So that's a not my problem?
Yeah. Yeah, but turbo codes great for, they're superior for the smaller codes.
Any other questions?
Yeah. Well, Michelle, you'll be very happy to know that ham radio does use LDPC codes. One of our most favorite high-frequency digital communication modes, FT8, uses LDPC.
Yes, it does.
And what's amazing about it is that in each message transmission, which lasts about 12.6 seconds, we get the message decoded in 15 seconds. That's pretty darn quick. So my question is, are there some code word structures that take longer than others?
That's a really good question.
Yeah.
Are there some code word constructions that take longer than others? I'm going to say yes. Unless Bob wants to correct me, because he might know, because he knows a lot about LDPC. But yeah, I mean, you can mess up your code in several ways. I've told you how you can mess it up with a 4 path, and you can mess it up by taking the H, generating a the null space, and then picking a crappy code generation one. Yeah, you can trash it that way. I mean, just have too many errors and you'll tank it. And yeah, for the regular ones that are all kind of symmetric, it's not that big of a deal. But if you have an irregular one and you just happen to get a whole bunch of errors on the ones that don't have good coverage, then your convergence may kind of not fail, especially if you're being kind of stingy with the number of iterations. Does that make sense? Yeah. Yes, sir.
Yeah, so a lot of newer chips, like phone system on chips, and I think even down to microcontrollers, they're starting to add AI and machine learning accelerators in there. A lot of this stuff like vaguely reminds me of some machine learning stuff. Do you think there might be some way to shoehorn this hardware into accelerating LDPC codes?
Yeah, there are some that where they. I mean, so the first answer I'll give you is that just pragmatically speaking, that there is a lot of machine learning and AI that's used in code generation, or is starting to be used in code generation. And I've blundered across papers that talk about it. So that's not a part of the field that I am an authority on, but I think the answer is yes, and I think your instincts are right, and I think there's plenty of room in LDPC codes for machine learning to really make a big difference.
Okay, one more question up front.
On your G and H matrices, I just wondered if anybody's looked at what the eigenvalues and eigenvectors of those are, and do they follow in some particular pattern?
To follow a particular pattern. The pattern that they follow is that they are those, and that they're defined. And so I don't know. You know what? It sounds like that your question is deeper than it sounds at first. We have so much in common. I'm going to look that up. Yes, sir. Yes. Yeah. Yeah, they are pretty straightforward. Like, it's because of the sparsity. Wow, there was a lot of slides. Do I win the award for like the most number of slides?
No.
Oh, yeah, this one. Oops, maybe one more. Yeah, this for any because even though this isn't strictly speaking an LDPC, but it's so sparse that like they pop right out. Like they're just there.
So Scotty, you got one more question?
Yeah, I was just wondering if you changed the encoding on a per frame basis, how do you do the decoding?
If you change the
you said you could change the encoding on a per frame basis, like to the path changed or the characteristics changed. So how do you change the encoding?
That's a really good question. DVB is super cool here. So the frame has a header, and the header is a known, stable, stays the same modulation. It's pi over 2 BPSK, really pretty cool. And pi over 2 BPSK, very simple, and it allows you to do something called differential decode or differential receive. Very, very simple, easy decode, right? So you get a frame, you have no idea what the coding is or even the modulation, right, on the rest of the payload. But you know that the header is this pi over 2 BPSK thing, and you've got these big pilots that are just, hey, here I am, and you've got a correlation word. I mean, it's given you all the lights and sirens to find it. You find it, and you decode the header, and the header tells you the details that you need. And if it's just not something you can decode, then you just wait for the next one, and that you tell your payload, hey, can you give me more help?
Yeah, because it would seem like if you didn't get that header, then
then you would only be able to decode what you could hear. And that's fair too, you know. But you want to have total information awareness about all the frames coming at you. The way that the payload would decide, or the way that they do it in DVB S2 and S2X for ACM, is either it's set or it rides the SNR. So you report how well you can hear, and the payload knows how loud you are, and it's like, well, you know, you take what you know and you figure it out, and here's the set of codes that are going to get you the best bandwidth. Since the symbol rate is fixed, the data rate and the coding are the other ends of the seesaw. And because the symbol rate's fixed, then all of the RF is a lot easier. It's much less to change, you know. So you have a very stable, big pipe coming at you. So that's how you decide on a per frame basis. Now you don't have to. That's kind of like advanced. You can pick one and set it, or you can have the equivalent of like a variable coding and modulation is another one, where there's a dial somewhere. Somebody's figuring out, they change it seasonally, for instance. Like for a lot of microwave deployments, it really kind of depends on the foliage and the weather and rain fade and stuff like that. You know, so you can change the coding, you know, seasonally or because of some sort of weather condition. Or you can go totally automatic ACM and have it just the SNR reports make it ride, and you get every last bit that's coming to you.
Okay, thank you very much.
Oh, you're welcome.